Hi Year 12. Today's video is having a look at 8D, which is investing money by regular installments. So some investment schemes such as superannuation are financial instruments called annuities, and these are savings that involve a regular contribution of funds to an overall invested amount that's growing basically, hopefully, over time from compound interest and other returns. So this would be the case where, for example, $1,000 is added to this fund every year and it's compounded over a certain number of years that are known. Hence, superannuation. So you may not know a lot about how superannuation works. We're going to do some modelling of that today, and it's more the people in standard that call them annuities, but that's what we're basically looking at today. Now, our series that we're going to have a look at, we're actually going to work backwards. So the best way to look at it is to actually work through an example. Investment schemes like superannuation require money to be invested regularly. So it might be fortnightly, monthly, or yearly. So if you're working and you're being paid fortnightly, you're generally adding money, or your employer is adding money to your superannuation fund every fortnight. This means each individual instalment will earn compound interest for a different length of time. So to calculate the value of these, we need to use our knowledge of the geometric progression. So let's have a look at below. We're going to have a look at one below here on the left-hand side. So we're saying that a sum of $2,000 is invested at the beginning of each year in a superannuation fund. Now, the beginning is important here because in our next example, we're not investing at the beginning of the year. So like a lot of our other questions, the language is going to be really important. So $2,000 at the start of each year, interest is paid at 5% per annum, and money will be available at the end of 30 years. So generally in a superannuation fund, sorry about the background noise there, I'm doing these videos at school and there's a lot of noise there. So what we're looking at here is $2,000 is being contributed in. We've got 5%, it's per annum, and our years are years. So these are in equivalent timeframes. And what we're going to look at is the formula for compound interest that we looked at last lesson. So A equals P1 plus R to the end, and our rate of 5%, we divide by 100 to get 0.05. So when we invest our first $2,000, we're going to think of it like this is in our first year. That $2,000 is being invested into that fund for 30 years. So 1 plus 0.05 is 30 times by 200, and this neatens up to this part here on the right. So with these questions, we know what the end date of the investment is going to be. So in year number 2, we're investing another $2,000 at the start of the year, but that $2,000 is only being invested for 29 years. And we're going to continue doing that until the 30th year, when at the start of that 30th year, we put in our $2,000, and that $2,000 is only being invested for that 1 year. So each year we have a compound interest formula to deal with. So that's an individual year, but if we wanted to work out what the total sum of our fund is going to be, that's our next step, and that would be summing all of those A's up here from 1 down to 30. So the sum to 30 would be the sum of all our individual A's for each year, and if we write it out like this, I've just put in the 30, the 29, all the way down to 1 that we had written up above in green, and then I've factored out 2,000. So I've got 2,000 times by all of my 1.05 to the 30, all the way down to the 1. And then what I've done is I've just flipped it around to make it look more like a geometric progression that we're used to. So I've just popped the 1 power down this end, and I've written the 30th power at the other end. So what you can see we have is a $2,000 out the front, but in the brackets we've got a geometric progression. So we can sum this geometric progression, get a solution, and times that by 2,000. So the sum of a geometric progression of which we have A as 1.05 and our ratio is 1.05 and N is 30, where R is greater than 1 is our formula here that we need to use. I pop these 3 things into my formula and I'm going to get a sum of 69.760789. That is the sum of this part here in the brackets. I'm going to times that then by 2,000. And I'm going to get the total value of my investment after 30 years. So I've got $139,521.58 as my total. Now we're going to have a look at the second question. And this one's a little bit different. a little bit harder, and you need to think a little bit about this one, about what's happening. So an amount of $100 is put into an investment account at the end of each month. So before we had at the start of each month, and here it's at the end of each month. So for that first month, that $100 isn't earning anything. It's not earning until the start of the second month, basically, and through that second month. So if interest is paid at 12% per annum, and it's paid monthly in this case, how much is the account at the end of 8 years? So we need to change our years to months. We need to change our percentage to months. And I've done that down here, but I just wanted to note the orange part here. It says at the end of the first month is the same as the start of the second month. So we're basically missing one time period for the compounding of interest. And I'll show you what that does to our progression down below. So our rate is 12%, divided by 12, so it's 1% per month, which we divide by 100, and we end up with 0.01. So that's our monthly percentage. Now for n is 8. 8 times 12 is 96. So we're going to have 96 A's, so 96 different accumulated amounts for our compound interest. But because we're popping in at the end of the 8th month, our powers, I've taken one off, and we're going to only have powers up to 95. And our first one is going to be a power of 0. So we need to just think a little bit about what's happening when we're working these ones out with the end of the month ones. So our sum's going to be all our individual monthly accumulations. So the first month, we've popped our $100 in, and it's getting 1 plus 0.01 to the power of 95. So remember that first $100 is not put in at the start of the month, so it's not getting interest in that first month. So we've popped the 95 in there instead. The second month we're down to 94, and I've just written the Neaton versions up here to the side. Now we're going down all the way to 96 still, but 8 of the 95 is going to have a power of 1. And our 8 to the 96 is just going to be 100 because it doesn't have any accumulation of interest. Yeah, so I'll say that last part again. In that last month, the 96th month, that $100 is put in at the end of the month, so it has not gotten any interest. So that's why I've got a 0 power in that one. So if we simplify the right-hand side here and add all our A's together, I've done that and just factored the 100 out right at the start. I'm going to get 1.01 to the 95 all the way down to 1, which was this bracket here to the 0. Anything to the 0 is 1. So when I flick my sequence around, my first term now is 1. My last term is the 1.01 to the power of 95. So just be really careful in doing these end of month ones, or end of period installments, that we're going to get an A most generally as that first term. The ratio is still the 1.01. So when we're summing this one up, just be careful. And we're going to end up with our S to the 96 being our sum of the series times 100. So there's my 159.927 is my sum of that geometric series. So just check that you get that in your calculator. Popping that times 100, we're going to end up with $15,992. Now that should be enough to get you through the work, but I've popped another example in here. So if you feel that is enough and you don't want to look anymore, don't, but I'm going to go through this one. So Robin invested $10,000 into a superannuation scheme on the 1st of July each year, beginning in the year 2010. The money earns compound interest at 8%, compounds it annually. So we've got years and years. How much will the fund amount to by the 30th of June 2030? So the 30th of June is the same as the 1st of July. Okay, the end of the 30th of June is the same as the start of the 1st of July. And we've got from 2010 to 2030, we've got 20 years. So it's a fairly simple one, and it's at the beginning of the year. So it's like that first example that I did above. So we've got our A1 down to A20 is going to be 10,000 times. Now I can write it as, I kind of did it a little bit, did it backwards to the way I did it before, because once you get into the scheme of things, you can see that. So really, my A1 is the number that I've got down here, 10,000 times 1.08 to the 20. And here's my first term here. Factoring out the 10,000 like I did above, there's my series. I'm going to times my series sum by 10,000, and I'm going to end up with 494,000. So if you want to pause the video and see if that you can get up to that point, that would be great. Now, how much will the fund amount to in N years? So in N years, we want to look at the sum. So we've got the sum to N is going to be 10,000 times what I had up here without the 20 in it. So I'm going to take the 20 out and pop an N in there, and the rest of it's going to stay the same. So 10,000 divided by 0.08 is 135,000 times this part in my bracket here. Okay. And this is the solution, because the sum to N, we don't know what it's going to be. It'll just depend on what our N is going to be. Part C says, show that 2031 is the year when the fund will first exceed $500,000. So I would not do anything too fancy for that question. I would pop in the fact that 2031 is the 21st year of the investment. If I pop that into my generic N up here, I'm going to end up with 544,000, which we can see is going to be the first year because we're introducing to our fund 10,000 a year. That's the answer that we need. You could also pop S to the sum to 20 in there as well and show that that is under that amount if you would like to, and that would probably be a better idea. Okay, it says what annual installment would have produced $1 million by 2030? This is the question part that I wanted us to look at for this one. This is the most important part. So the annual installment instead of $10,000, I want to figure out what that was. So what I've done is look up what I've got above at part B, and I'm basically wanting to find what A was in there. So the sum to N is equal to A, and that's going to stay at 20 because the question did say by the year 2030. So we're still looking at that being 20 years away. So what we're basically wanting to do is pop our sum to N as 1 million, and we're going to rearrange our formula to get an A value. So I've popped this side in my calculator, I've divided by my values of 1.08 divided by 0.08 over this side, and then I've divided by the part in the bracket, and I've ended up with this value in here. Sorry, which you can't see very well there, I don't think. So my annual installment would be $20,233.53 to get $1 million as my sum.